Welcome to Science Listener. Imagine standing at the edge of the universe where galaxies are scattered like quiet lanterns across an infinite night. The stars burn, the nebulae glow, but behind it all lies something far larger. A silence filled not with emptiness, but with mysteries we cannot see. So before you settle in, don't forget to press like and subscribe. But only if you're curious how most of reality is invisible and how science tries to grasp it anyway. And leave me a comment. Where are you listening from and what time is it? It's uncanny to think of someone drifting off to this cosmic tale in Tokyo while someone else in Sao Paulo is just pouring coffee. Now close the shutters, get comfortable, and let's descend into tonight's story. At first it feels steady, almost eternal. Galaxies drifting apart, stars circling their centres, light bending in patterns we can trace. But then comes the realization, what we see is not enough. The math doesn't add up. The motions of galaxies betray a hidden weight, and the expansion of space itself accelerates as if pushed by a ghostly hand. 95% of the universe is invisible to us. We live among shadows we cannot touch. People have imagined this unseen as new forms of matter, as energy woven into the fabric of space itself, as something that binds and something that tears apart. Today, we call them dark matter and dark energy, not because they are evil or cursed, but because they refuse to reveal themselves. They are the scaffolding and the breath of the cosmos, shaping what we see and what we cannot. In this journey, we will move step by step, from the strange evidence that first revealed their presence, to the particles and fields that might explain them, to the destiny they dictate for every star and planet. Dark matter and dark energy are more than terms. They are the stage on which all of cosmic history unfolds. Close your eyes and imagine. A lone galaxy, drifting through blackness, its stars circling an invisible anchor, while far beyond its edge space itself stretches faster and faster. The universe holds its breath, waiting, as if it knows that its deepest secrets remain just out of reach. And that is where our story begins. The silence of that vision remains, yet it carries weight. It presses on your thoughts like a hidden hand, reminding you that the stage of the universe is not built from the stars you see, but from something far greater, something invisible. When you tilt your head to the night sky, you trust your eyes. You think you're seeing the universe, a complete picture, glittering with constellations and the faint shimmer of the Milky Way. Yet what your eyes show is only a sliver of reality. Astronomers today can tell you with unsettling precision, everything you see, everything that burns or shines, every atom of your body and planet makes up less than 5% of existence. The rest, a staggering 95%, hides in shadow. It is not dark because it is evil, but because it refuses to meet your gaze. The first clue came in 1933 when Fritz Zwicky peered at the Coma cluster. He measured the velocities of galaxies and realized they were racing faster than the gravity of visible matter should allow. According to the physics of the day, the cluster should have torn apart, flinging galaxies into the void. Instead, they clung together as if wrapped in a cloak of invisible mass. Zwicky called it Dunkel Materie, dark matter. His colleagues dismissed him. The numbers seemed wild, the idea absurd. Still, the seed was there. The universe was heavier than it looked. 4 decades later, the riddle returned with even greater force. Vera Rubin and Kent Ford traced the rotations of spiral galaxies in the 1970s. By all logic, stars at the edge should have moved slowly like outer planets orbiting far from the sun. Instead, they raced around as if an unseen hand pushed them. The pattern was unmistakable. Galaxies carried vast halos of mass that emitted no light. Rubin's quiet persistence turned Zwicky's lonely suspicion into a fundamental problem of cosmology. Dark matter became the invisible glue of the cosmos, unseen, untouchable, but written into every orbit and every gravitational pull. And yet, as this puzzle gained weight, another force emerged from the data, more elusive still. By the end of the 20th century, astronomers realized the expansion of the universe itself was not slowing, but speeding up. Something, not mass but energy, was stretching space apart. If dark matter binds, dark energy tears away. They are not the same, though both hide from your senses, shaping a universe where you see only the surface of a deeper design. So you lie back under the stars thinking you see it all, when in truth you live in a thin film of light atop a sea of shadows. 95% of reality moves around you, through you, and you cannot touch it. The question sharpens, unavoidable. Will we ever truly see what the universe is made of? The search for an answer begins with the division, because what hides in the dark is not one thing, but two, one that pulls and one that pushes. Astronomers gave them separate names, dark matter and dark energy. As if naming could tame the enormity of the unknown, the words sound alike, yet they describe different rulers of the cosmos. One keeps galaxies bound, the other drives the very fabric of space apart. You notice the first in the quiet discipline of gravity. Look at a galaxy like the Milky Way. More than 100 billion stars circle its center, yet the ones at the edges move far too fast to stay bound by visible matter alone. If only ordinary mass existed, the outskirts would fray, and those stars would slip into the void. They do not, because something unseen provides the extra grip. This is dark matter, about 27% of the universe, silent but insistent, like weight pressing on your shoulders though no hand rests there. The second reveals itself only when you stretch your gaze across billions of light years. In the late 1990s, two independent teams studied type Ia supernovae, exploding stars so bright that they serve as cosmic lighthouses. Their light carried the story of how quickly the universe was expanding. The results, announced in 1998, shocked the scientific world. The expansion was not slowing under gravity's pull, as expected, but accelerating. Space itself was stretching faster and faster. That mysterious pressure became known as dark energy. Today, it is thought to make up about 68% of everything, a background force woven into the very fabric of space-time. So you live between two unseen rulers. One anchors galaxies together, bending light, shaping clusters, holding cosmic webs in its grip. The other pulls them apart, ensuring that no matter how tightly matter clings, the distance between great islands of stars grows. You are caught between them every time you raise your eyes to the night sky. The tug of one steadies your place, while the push of the other ensures the horizon runs from you faster than you can chase. The distinction between the two is not academic. For decades, astronomers argued whether the strange motions of galaxies could be explained by modifying gravity rather than inventing invisible matter. The modified Newtonian dynamics, MOND, hypothesis suggested that perhaps gravity itself worked differently on cosmic scales. Yet evidence stacked higher. Galaxy clusters heavier than light could account for, gravitational lensing bending starlight in ways visible matter could not explain, and finally the bullet cluster collision in the 2000s showing mass and visible gas separating under impact. These were not the tricks of altered equations. Something invisible had weight, dark energy stood apart, demanding its own explanation. It was not discovered by studying small scales, but by reading the story of the universe's expansion. Supernovae whispered it first, then the cosmic microwave background confirmed it. To make the universe look as flat as it does, a repulsive energy was needed to balance the books. Unlike matter, its density did not dilute as space expanded. Even as galaxies drifted farther apart, dark energy remained almost constant, dominating more and more of the total. That is why the acceleration grows, why distant galaxies recede faster than near ones, why the future of the cosmos seems locked into endless flight. You feel it not directly but through consequences. Without dark matter, the Milky Way could not exist as it does. Without dark energy, the expansion of the universe would have slowed, perhaps even reversed. With both present, your night sky is an uneasy balance. Structures form and grow under invisible weight, while the vast distances between them are stretched wider with every tick of cosmic time. Numbers carve the difference into sharp relief. Roughly 5% of the cosmos is baryonic matter, the atoms of hydrogen, helium, oxygen, carbon that make up stars, planets, oceans, and lungs. 27% is dark matter, unseen, cold, massive. 68% is dark energy, diffuse, omnipresent, relentless. These are not rough guesses. The Planck satellite mapping the cosmic microwave background in 2013 confirmed the proportions with striking precision. Every ripple in that faint afterglow of the Big Bang carried the fingerprint of matter and energy, both visible and hidden. So when you breathe on a cold night and watch the vapor rise, know that the air you exhale belongs to a category so rare it is almost trivial on the cosmic scale. The atoms that carry your life are outnumbered by the weightless stretch of dark energy and the unseen mass of dark matter. You walk through a universe that is mostly not what you touch. You lie under stars that shine only because a deeper balance holds them. You listen to this story in the warmth of a room, while outside galaxies slip away faster than light itself could catch. And the lesson is clear. What binds you is not what pushes you away. The universe hides two shadows, not one, and both are written into your every glance at the sky. To make sense of these shadows, astronomers built a framework, a model that stitches together every clue from galaxies, radiation, and expansion into one story of the cosmos. They call it lambda cold dark matter. It is not a poetic name, but it carries the weight of decades of measurements. Every major discovery about the unseen universe eventually folded into this model, until it became the map by which modern cosmology travels. Lambda is for the cosmological constant, Einstein's idea from 1917 that space itself could contain an energy density. At the time, he introduced it reluctantly, only to hold the universe steady against collapse. Decades later, when expansion was discovered, he abandoned it, calling it his greatest mistake. Yet the accelerating universe of the 1990s revived lambda in a new light. It became the simplest way to represent dark energy, a term for the steady push embedded in space-time. CDM is for cold dark matter, a phrase chosen to mark the difference from fast, hot particles like neutrinos. Cold means that these unknown particles move slowly compared to the speed of light, so they can clump and form structures. Without this slowness, galaxies would not have condensed as they did. Simulations that begin with cold, dark matter and a little ordinary matter grow filaments, clusters, and voids that look strikingly like the real cosmic web mapped by telescopes. The model took shape gradually. In the 1960s and 1970s, astronomers first recognized that visible matter could not explain galactic motions. In the 1980s, as computer power grew, simulations showed how dark matter could weave the skeleton of large-scale structure. By the 1990s, the combination of supernova measurements, galaxy surveys, and observations of the cosmic microwave background made it clear any model that ignored both dark matter and dark energy failed. The lambda CDM picture became the standard, not because it explained everything, but because it explained the most with the least. Measurements confirmed its outlines again and again. The UMAP satellite in the early 2000s traced the cosmic microwave background and revealed the first high-resolution map of tiny temperature fluctuations left from the Big Bang. These ripples carried the fingerprint of matter and energy contents. The Planck satellite in 2013 sharpened the picture even further, giving the most precise values yet: about 5% ordinary matter, 27% dark matter, and 68% dark energy. The universe looked flat on the larger scales, just as lambda CDM predicted. Still, the model is not perfect. It is a scaffolding, not a final building. On small scales, problems appear. The missing satellites issue, the cusp core problem in galaxies, tensions between predicted and observed distributions, and there are broader cracks. The Hubble tension, a disagreement between local measurements of the expansion rate and those inferred from the early universe, hints that something in the model might be incomplete. Some physicists argue that lambda CDM is a framework stretched thin, powerful yet temporary, like scaffolding that will one day be replaced by a deeper theory. Yet no alternative has matched its breadth. MOND adjusts gravity but cannot explain the bullet cluster. Exotic models of interacting dark energy or warm dark matter bring interesting variations, but they lack the consistency that lambda CDM shows across multiple datasets. When satellites, telescopes, and simulations speak, their voices align most clearly within this model. You stand beneath the night sky, and while your eyes show constellations, lambda CDM supplies the deeper map. It is a model in which galaxies form because dark matter clings unseen, and expansion accelerates because dark energy pervades space. It does not tell you what these entities are, only how they behave. In this sense, it is like a shadow traced on a wall, sharp in outline, uncertain in substance. The cosmos we navigate today is drawn by lambda CDM, a framework that holds until a better one arrives. The question lingers: if the framework works so well, will the shadows it describes ever step into the light? Science has always moved from hints to evidence, from indirect traces to direct encounters. Electricity was once nothing but sparks on amber, atoms once only ideas in Greek philosophy. Could dark matter and dark energy, still faceless after decades of study, follow the same path into clarity? Dark matter has drawn the most persistent hunts. Since the 1980s, enormous detectors have been buried beneath mountains and deep mines, shielded from cosmic rays by rock. Inside them sit tanks of liquid xenon or crystal lattices chilled to near absolute zero, waiting for the faintest collision between a passing dark matter particle and an atomic nucleus. Projects like Xenon 1T in Italy and Lux in the United States have listened in silence for years, registering rare signals, teasing anomalies, but offering no unambiguous discovery. The detectors grow ever larger, the hope ever sharper. One day, a particle may leave its fingerprint in the stillness. Other approaches look to the sky. Gamma-ray telescopes search for excess radiation from regions dense with dark matter, like the galactic center or dwarf galaxies. If dark matter particles annihilate when they meet, the afterglow might betray them. Neutrino observatories watch the Sun, hoping that dark matter captured in its core could produce faint streams of high-energy particles. Even the Large Hadron Collider has joined the chase, smashing protons together with such energy that if exotic particles exist, they might appear in the debris. Each run ends with new limits, drawing tighter circles around what dark matter could be. Dark energy presents an even deeper challenge. It does not clump or collide. It spreads smoothly, almost evenly, across all of space. No detector can capture a particle of it, because it may not come in particles at all. Its presence is read only in the motion of galaxies and the shape of large-scale structure. That is why massive projects like the Dark Energy Survey, the Sloan Digital Sky Survey, and now the Dark Energy Spectroscopic Instrument, DESI, map the cosmos with breathtaking detail. By charting how galaxies cluster and how expansion changes with time, they hope to sketch the fingerprint of this elusive force. You walk through a world where experiments reach beneath mountains, across deserts, and into orbit, all in search of what refuses to show itself. The very act of living in this century means carrying within your mind the awareness that most of existence remains invisible. When you raise your eyes to the night sky, you're not just stargazing. You're looking at a mystery that thousands of scientists working across continents are trying to name. Skepticism remains. Some physicists argue that perhaps the shadows will never be seen because they are not real things, but signs that our equations are incomplete. MOND and other modified gravity theories continue to attract study, especially as the Hubble tension sharpens. Could it be that what we call dark energy is just a misunderstanding of gravity on cosmic scales? Or that dark matter is a placeholder for physics not yet written? These doubts keep the field alive, ensuring that every dataset is checked against the possibility that the standard model will one day fracture. Yet the history of science carries a warning. Invisibility today does not guarantee invisibility forever. Neutrinos were once ghosts, predicted in the 1930s and not directly detected until the 1950s. Gravitational waves were theory for a century, finally recorded in 2015 by LIGO. What seems unreachable can, with patience and invention, one day leave a measurable mark. Dark matter and dark energy may be the hardest quarry yet, but they are not without precedent. The search is not only technical but philosophical. To ask if the universe is knowable is to ask if human senses, extended by machines, can ever pierce the fabric of reality completely. The answer may be yes, given time. It may also be no, leaving certain truths beyond reach. Both possibilities carry weight. If discovery comes, the shadows will gain substance, and cosmology will move from mapping effects to describing causes. If discovery never comes, then science will live with a paradox, a universe explained by entities forever unseen. For now, the question remains open. You live in the thin slice of history when these mysteries are fresh, when the experiments are young, when no final verdict has been given. Generations ahead may read in textbooks what dark matter truly is, or they may inherit the same uncertainty. The only certainty is that the universe does not give up its secrets easily. And so the story pauses here, with detectors listening in the dark, telescopes tracing the edges of time, and theory reaching for what has not yet stepped into view. The question of whether we will ever see dark matter and dark energy is not answered tonight, but it continues to shape the way we look at every star above us. The mystery becomes sharper when you focus not on the galaxies themselves, but on the galaxies themselves, those great spinning islands of stars that should have flown apart long ago. You know the Milky Way as a steady arch of light across the night sky, But beneath its beauty lies a contradiction. By the rules of visible gravity, billions of stars on the outskirts orbit too quickly. They should have slipped away into the dark, scattering like sparks from a wheel. They remain, circling faithfully because something unseen holds them fast. This puzzle first revealed itself in the 1930s, when Fritz Zwicky studied the Coma cluster. He noticed that the galaxies inside moved with reckless speed, far too fast for the gravity of visible matter to contain them. Without additional mass, the cluster should have unravelled. Zwicky gave this missing weight a name, Dunkelmaterie, dark matter. At first, his claim was dismissed, too bold, too unsupported by technology of the time. Yet the problem never went away. 4 decades later, in the 1970s, Vera Rubin and Kent Ford returned to the question with sharper instruments. They measured the rotation curves of spiral galaxies, plotting how fast stars orbited at different distances from the galactic centre. By expectation, speeds should have dropped with distance, just as planets in the solar system move slower the farther they are from the Sun. Instead, the curves flattened. Stars at the edge moved nearly as fast as those near the core. The data left no escape. Something invisible added mass, stretching far beyond the luminous disk. You imagine standing on one of those distant stars orbiting the fringe of a galaxy. The pull beneath your feet should weaken, the sky should loosen, yet the grip remains steady. That grip is not from what you see, but from a halo of mass that emits no light, no heat, no radio signal. Without it, galaxies would tear themselves apart within a few turns of their spiral arms. The night sky you trust is a fragile illusion propped up by what cannot be seen. Modern surveys deepened the view. Radio telescopes traced the motion of hydrogen clouds. Infrared cameras revealed hidden stars, and every wavelength confirmed the same curve. Flat, stubborn, undeniable. The Milky Way itself, our home, sits wrapped in such a halo. It is the reason the spiral arms hold together, the reason clusters of galaxies cling in great webs rather than disperse into emptiness. Ordinary matter alone explains only a fraction. The rest belongs to this unseen scaffold. The concept is not abstract. It dictates the very shape of the universe. Simulations that include only visible matter produce a cosmos too loose, too chaotic, too empty. Add dark matter, and structure forms. Filaments connect clusters. Galaxies emerge like beads strung along invisible threads. Voids stretch vast between them. The cosmic web, mapped by modern surveys like the Sloan Digital Sky Survey, resembles the tangled roots of a forest seen from above. Without dark matter there is no forest, only scattered leaves. Dark matter does not shine, yet its fingerprints are everywhere. You see them in the arcs of light bent around massive clusters, in the steady speeds of stars circling galactic disks, in the persistence of galaxies themselves. It is the hidden glue of the cosmos, silent yet indispensable. Its reality is measured not by sight, but by the fact that without it, the night sky you know would collapse into disorder. And so the riddle of galaxies remains both simple and profound. They exist because something unseen holds them together. The most striking evidence for this unseen mass comes not from distant clusters, but from the very motions of stars inside galaxies. By the mid-20th century, astronomers had developed methods to measure how quickly stars and gas clouds orbited their galactic centres. The expectation was simple. Just as planets in the solar system slow their pace the farther they are from the Sun, stars at the edges of galaxies should orbit more slowly than those near the core. The pull of visible matter decreases with distance, so orbital speed should fall. Yet the universe did not match this expectation. When Vera Rubin and Kent Ford carefully mapped the velocities of stars in the 1970s, they found that the curves flattened. Instead of dropping as distance increased, orbital speeds remained nearly constant far into the outskirts. Stars that should have drifted away kept racing around the galactic disk as though gripped by an invisible hand. This was not a minor anomaly. It appeared in galaxy after galaxy, across spirals large and small, in data checked and rechecked. Radio observations confirmed the effect even beyond the reach of visible stars. Neutral hydrogen gas, which glows faintly in radio waves at a wavelength of 21 centimeters, extends far past the luminous disk. Astronomers traced its rotation and found the same stubborn pattern, flat curves stretching deep into the halo. The implication was undeniable. Galaxies were wrapped in halos of mass that gave no light yet carried weight, immense enough to hold them together. This discovery transformed the dark matter problem from speculation to necessity. Zwicky's claim in the 1930s had been bold but isolated. Rubin's data, supported by radio telescopes and repeated across hundreds of galaxies, left no escape. Either gravity itself required rewriting, or an unseen form of matter dominated galactic structure. For most, the second answer fit the evidence more cleanly. You walk through a night where the Milky Way arcs across the sky, serene to the eye, yet every star you see owes its place to this hidden mass. The rotation curves are not abstract graphs on paper, but the reason your galaxy has shape at all. Without that invisible halo, the spiral arms would unwind, and the thin disk would scatter into intergalactic dark. By the 1980s and 1990s, galaxy surveys extended the evidence further. Large telescopes in Hawaii and Chile recorded the motions of thousands of galaxies, finding the same flatness on scales too broad to dismiss. Clusters of galaxies too showed member galaxies orbiting at speeds that required additional binding mass. No longer could dark matter be treated as a footnote. It became central to every model of cosmic structure. Today, rotation curves remain one of the clearest signatures of dark matter. They are taught in classrooms, simulated in computers, and written into the very equations of cosmology. The line that should fall but stays flat is now iconic, a reminder that the universe holds more than light reveals. Every time the curve refuses to dip, it whispers the same truth. Galaxies endure because invisible matter anchors them in place. Another proof emerged not from the motions of stars but from the bending of light itself, as if the universe used its own beams to sketch the weight of the invisible. According to Einstein's theory of general relativity, massive objects warp space-time, bending the paths of light that pass nearby. This effect, called gravitational lensing, was first confirmed in 1919 during a solar eclipse, when starlight passing near the Sun appeared displaced. What began as a rare experiment soon became one of the most powerful tools for probing mass across the cosmos. When astronomers turned this tool toward galaxies and clusters, they saw distortions that visible matter alone could not account for. Background galaxies stretched into arcs, smeared into rings, or twisted into faint shapes by the gravity of intervening structures. In many cases, the luminous matter of those structures, stars and hot gas, was too little to create such strong effects. Something else, far heavier, was curving the light. Weak lensing revealed even more. By collecting subtle distortions across wide fields of galaxies, surveys built statistical maps of mass distribution. Patterns emerged that showed large clumps where little visible matter existed. These mass maps drew the outlines of halos, filaments, and clusters dominated by dark matter. The technique turned the night sky into a canvas where invisible weight painted its presence. The results grew more detailed in the late 20th and early 21st centuries. The Sloan Digital Sky Survey charted millions of galaxies, producing three-dimensional maps of the universe that revealed the cosmic web. Gravitational lensing confirmed that this web could not be explained by visible matter alone. Later, instruments like the Canada-France-Hawaii telescope and the Dark Energy Survey refined the technique, tracing dark matter with increasing precision. These maps showed that the invisible skeleton matched predictions from lambda-CDM simulations. You stand beneath that sky, thinking the stars are scattered at random, when in fact they trace filaments of mass shaped mostly by dark matter. Light from distant galaxies carries the imprint of the invisible, distorted ever so slightly as it travels billions of years to reach your eyes. What you see as a faint smear in a telescope is, in truth, a silent sketch of hidden weight. The beauty of gravitational lensing lies in its directness. It does not rely on assumptions about how stars move or how gas behaves. It measures gravity itself, bending light in ways geometry cannot fake. Each arc, each stretched image is testimony that mass exists where no light shines. The universe draws its own X-ray, exposing a framework no human eye can otherwise detect. Modern surveys now combine weak lensing with other probes, baryon acoustic oscillations, cosmic microwave background data, galaxy clustering, to refine the cosmic inventory. The consistency across methods strengthens the case. Dark matter is not a trick of equations, but a dominant component shaping the larger structures. The invisible becomes cartography. From the slight tilts of background galaxies, astronomers assemble maps of dark matter across billions of light years. These maps align with simulations, showing a universe built from filaments and knots heavy with unseen mass. The constellations you recognize are only bright beads on threads, spun mostly from what refuses to shine. The light itself proves the point. Every distorted galaxy is another line on the hidden map, every arc another trace of the scaffold. To follow those lines is to admit that the cosmos is bound not by what we see, but by what curves the light we depend on. The evidence grew even harder to dismiss when two massive clusters collided and revealed the separation between visible matter and hidden mass. This event, now known as the Bullet Cluster, was first observed in the early 2000s through a combination of X-ray images and gravitational lensing data. It offered a rare natural experiment. Two clusters of galaxies smashing together at tremendous speed, their components separating in a way that betrayed the presence of dark matter. Visible matter, mostly in the form of hot gas, slowed as the clusters collided. X-ray telescopes such as Chandra recorded this gas glowing at tens of millions of degrees, forming bright clouds where the collision forced it to heat and compress. Yet when astronomers mapped the gravitational lensing of background galaxies, the centers of mass appeared offset from these gas clouds. The bulk of the mass had passed through the collision almost untouched, while the luminous gas lagged behind. This was the smoking gun. If modified gravity alone explained galaxy motions, the mass and the light should have remained aligned. Instead, they parted ways. The stars, which are sparse and rarely collide, moved forward, and the unseen mass moved with them. The gas, which interacts strongly, was slowed and left trailing. Gravitational lensing revealed that the mass clung to the galaxies rather than to the visible plasma. Dark matter behaved as expected, collisionless, invisible, yet dominant in shaping gravity. You stand in thought before that image. Blue maps of mass overlaid on red clouds of gas, and see the story unfold. The light shows one picture, the gravity another. What your eyes receive is only the lagging debris. What the lensing proves is that most of the cluster's weight lies elsewhere. It is a picture that no adjustment of equations alone can explain. The bullet cluster became the touchstone for arguments about dark matter versus modified gravity. It showed directly that unseen mass is not just a trick of dynamics, but a separate component of the universe. Later observations of similar collisions, such as Max J 0025.4-1222, reinforced the case. In each, visible matter and gravitational mass separated, repeating the same conclusion. By the late 2000s, the bullet cluster stood as one of the most persuasive single images in modern cosmology. It condensed decades of indirect hints, rotation curves, cluster speeds, gravitational lensing, into one clear demonstration. Galaxies move with halos of invisible matter, and when clusters collide, those halos glide past each other like ghosts, while ordinary matter crashes and stalls. Simulations confirm the process. Models that included collisionless dark matter reproduced the observed separation. Those that tried to rely on modified gravity alone failed. The evidence was not just qualitative but quantitative, matching lensing maps and X-ray data with remarkable accuracy. The lesson is stark. When the universe stages collisions on scales of millions of light-years, it reveals the architecture of its contents. Ordinary matter is noisy, collisional, luminous. Dark matter is quiet, invisible, unyielding. Together they create the sky we know, but apart they show their true natures. The bullet cluster still shines in textbooks and lectures as a milestone, a reminder that sometimes the cosmos arranges experiments no laboratory could perform. In those images of displaced light and mass lies a truth impossible to ignore. Galaxies and clusters are bound by a form of matter we cannot see, yet cannot do without. The next step in the story turns from evidence to speculation, from the weight we measure to the identities we cannot yet name. Dark matter proves itself again and again through gravity, through the orbits of stars and the bending of light, yet it never shows its face. To explain it, physicists proposed an entire menagerie of invisible particles, ghosts of theory, conjured from equations and silence. They are sometimes called phantom particles, because no detector has ever captured them, no telescope has ever recorded their glow, and no experiment has heard their signal. By the late 20th century, the most favoured idea was the WIMP, weakly interacting massive particle. The name sounds almost playful, but behind it lies serious physics. A WIMP would be heavy compared to ordinary particles, carrying mass enough to account for cosmic structure, yet so reluctant to interact with light or matter that it would slip through your body without leaving a trace. The attraction of the WIMP idea was the so-called WIMP miracle. According to calculations in the 1980s, if such particles formed in the early universe, their numbers would naturally freeze out at exactly the right density to match the observed amount of dark matter. It seemed almost too perfect. The universe might be telling us directly which particle to look for. Others turned to even stranger candidates. In the 1970s, theorists proposed axions, named whimsically after a brand of laundry detergent because they cleaned up problems in quantum chromodynamics. Axions would be incredibly light, nearly massless, but produced in such vast numbers that together they could outweigh ordinary matter. Unlike WIMPs, axions would hardly interact at all, except perhaps by converting into photons in strong magnetic fields. To search for them, experiments built resonant microwave cavities, hoping to catch the faint whisper of a photon born from an axion's transformation. More radical still were sterile neutrinos, a hypothetical extension of particles already known. Ordinary neutrinos, elusive, nearly massless, flooding the cosmos by the trillions, had already been detected after decades of effort. Sterile neutrinos would go one step further. They would not even interact through the weak nuclear force, only through gravity. Their existence would stretch the standard model of particle physics, yet they could explain anomalies in neutrino experiments and provide the right cosmic weight. Each candidate grew from both necessity and imagination. The evidence demanded something beyond ordinary matter, yet the equations left wide freedom for invention. To speak of dark matter in the 1980s and 1990s was to walk a line between certainty that it existed and uncertainty what it actually was. Physicists filled that space with proposals building detectors under mountains, tuning radio antennas, and smashing particles in colliders, all in the hope that one of these phantoms might reveal itself. You live in the middle of this hunt, surrounded by headlines announcing possible signals and later attractions. One year, an underground detector records an unexplained event. The next, another group fails to confirm it. Rumours swirl of excess gamma rays, unexplained X-ray lines, mysterious fluctuations, yet none have crossed the threshold of proof. The phantoms remain, slipping past every attempt to pin them down. The phrase phantom particles captures both frustration and allure. They are invisible, untouchable, yet they haunt our theories like figures behind a curtain. Without them, galaxies unravel. With them, the cosmos makes sense. The search continues because absence itself is not enough to erase necessity. Every orbit traced by a star, every arc of light curved by a cluster, insists that something is there, waiting for a name. Among the many ideas, 3 candidates became the focus of decades of study: WIMPs, axions, and sterile neutrinos. Each arose from a different corner of physics, and each demanded its own style of experiment. The WIMP, or weakly interacting massive particle, dominated attention through the 1980s and 1990s. It fit elegantly into theories that extended the standard model of particle physics, particularly supersymmetry. A WIMP would carry mass heavy enough to sculpt galaxies, yet it would interact with ordinary matter only through the weak nuclear force and gravity. The appeal of the idea was the so-called WIMP miracle. When physicists ran the numbers, they found that if such particles were created in the hot furnace of the early universe, their abundance would naturally freeze out at a level matching the measured density of dark matter. The universe seemed to be hinting directly at the answer. Detecting a WIMP, however, proved daunting. Because it interacts so rarely, it can pass through the Earth, through mountains, even through your body without leaving a trace. To catch one requires vast detectors hidden deep underground, shielded from cosmic rays and radiation. Experiments like Lux in South Dakota and Xenon 1T in Italy filled enormous tanks with liquid xenon, waiting for the faintest flash of light or recoil of an atom caused by a WIMP collision. Each event was rare, ambiguous, easily confused with background noise. Yet year after year, scientists pushed forward, refining techniques, scaling detectors to ever larger sizes. The axion came from another path. In the 1970s, physicists struggled with the strong CP problem in quantum chromodynamics, the theory of how quarks and gluons interact. A new symmetry could solve the issue, but it implied a new particle, the axion. Light, nearly massless, yet produced in astronomical quantities, axions could drift invisibly through space and still outweigh stars when counted in the trillions upon trillions. They might convert into photons in the presence of strong magnetic fields, a clue that inspired ingenious experiments. The ADAMEX project in the United States, for example, built resonant microwave cavities cooled close to absolute zero. The hope was that axions entering the cavity might transform into microwave photons, leaving a faint signal against the silence. Each scan tuned the cavity to a different frequency, like twisting a cosmic radio dial, searching for a note from the invisible. Sterile neutrinos stretched the imagination further. Ordinary neutrinos had already proven themselves ghostly, interacting so weakly that trillions pass through your body every second without effect. In the 20th century, they were first proposed by Wolfgang Pauli in 1930, and finally detected in 1956. Later experiments showed they have tiny masses, a revelation that required physics beyond the standard model. A sterile neutrino would go even further, refusing to interact through the weak force at all. It would reveal itself only through gravity and through its subtle influence on oscillations of the three known neutrino types. Hints of anomalies in reactor neutrino experiments and X-ray emissions from distant galaxies have kept interest alive. A sterile neutrino with a mass in the kilo-electron-volt range could explain both dark matter and puzzles in neutrino physics. Each of these candidates inspired a global network of searches. The Large Hadron Collider in Geneva tested supersymmetry, hoping to find WIMPs among the debris of high-energy collisions. Underground detectors expanded year by year, with Xenon 1T and its successors reaching sensitivities unimaginable a generation earlier. Radio telescopes and microwave experiments tuned for the faint hum of axions. Space telescopes like XMM Newton and Chandra scanned for unexplained X-ray lines that could hint at sterile neutrino decay. Yet despite decades of effort, no definitive detection has arrived. You live in an age where announcements rise and fall. 1 month brings rumours of an excess signal in gamma rays near the galactic centre. Another speaks of a 3.5 kilo-electron-volt X-ray line spotted in clusters of galaxies. Later, analyses cast doubt, eroding the excitement. Each supposed breakthrough ends in debate. Each claim dissolves under scrutiny. Still, the searches continue, because the universe itself demands it. The evidence for dark matter's weight is overwhelming. The candidates remain shadows, but shadows pursued with relentless patience. The story of WIMPs, axions, and sterile neutrinos is not only about physics but also about endurance. Laboratories under mountains, satellites orbiting Earth, accelerators spanning kilometers, all of them strain to hear whispers from particles that may never speak. The effort itself has become part of the legacy of science, a reminder that the greatest mysteries resist easy answers. For now, the three candidates remain possibilities, each with strengths, each with unanswered questions. Whether the universe chose one of them or something stranger still is not yet known. But every orbit of a star and every arc of bent light insists that the answer is waiting. Among the stranger ideas stood a proposal that dark matter might not be particles at all, but ancient black holes born in the first moments after the Big Bang. They are called primordial black holes, or PBSS, and unlike the giants formed from collapsing stars, they could range from microscopic sizes to masses heavier than thousands of suns. The theory suggested that density fluctuations in the newborn universe could have collapsed directly into black holes, leaving behind a population invisible, yet massive enough to account for the missing weight. The attraction of this idea lies in its simplicity. No new particles need to be invented. General relativity already allows black holes, and the conditions of the early universe could, in principle, have created them. If they exist, they would drift unseen through space, adding mass without light, mimicking the effects of dark matter. Some physicists even suggested that PBHS could form the halos around galaxies, anchoring their structures just as particle dark matter would. Evidence for or against them has been sought for decades. Microlensing surveys in the 1990s, such as the Macho and Eros projects, searched for brief brightenings of distant stars as compact objects passed in front, bending their light. The results showed that while some compact objects existed, they could not make up all of dark matter. Still, small windows of possible masses remained. Later, with the launch of gravitational wave observatories like LIGO and VIRGO, new hints emerged. In 2015, LIGO detected the first merger of two black holes, each around 30 solar masses. Their unexpected size sparked speculation that they might be primordial, relics from the early universe. If so, perhaps many more like them populate the cosmos unseen. The idea remains controversial. If PBHs were too abundant, they would disrupt the cosmic microwave background, scatter light in ways not observed, or produce too much radiation as they evaporated through Hawking radiation. If they were too rare, they could not explain dark matter's weight. Observations of wide binaries, star clusters, and the cosmic background have narrowed the mass ranges where PBHS might still hide. Today, possibilities remain in certain windows. Very small black holes lighter than asteroids, or heavier ones of tens to hundreds of solar masses. You picture a galaxy halo not filled with particles, but with countless silent black holes, each tugging at stars, bending light, merging occasionally in bursts of gravitational waves. The night sky would look unchanged to your eyes, but beneath it a different architecture would govern. Instead of phantom particles, gravity alone would carry the mystery, written in collapsed relics from the dawn of time. The search continues. Surveys like Subaru's Hyper Suprime Cam scan the skies for microlensing events, while LIGO and Virgo expand their catalogues of black hole mergers. Each new detection sharpens the debate. Are these black holes stellar in origin, or could some be primordial? No definitive answer has emerged, but the possibility keeps the idea alive. Primordial black holes remain a candidate because they require nothing exotic beyond what we already know: gravity, collapse, and the violence of the early universe. Yet simplicity is not certainty. They may account for a fraction of dark matter, or perhaps none at all. What they offer is a reminder that the search for the unseen is not limited to the invention of particles. It may also demand we look again at the forces and objects already known, asking whether they can wear unfamiliar masks. Decades of effort have passed, detectors have grown vast, surveys have scanned the skies, and still no candidate has revealed itself with certainty. This absence does not weaken the case for dark matter itself. The gravitational evidence remains overwhelming, but it sharpens the paradox. The universe insists on hidden mass, yet every direct attempt to touch it ends in silence. Underground laboratories stretch deep beneath mountains, filled with tanks of liquid xenon or argon, listening for the faintest recoil of a nucleus struck by a passing WIMP. Years pass, signals flicker, anomalies appear, and then fade under further scrutiny. The Xenon 1T experiment once reported an excess of events that stirred excitement, only for new analyses to leave the matter unresolved. Larger successors like Xenon T stand ready, but none has yet declared a definitive discovery. Microwave cavities tuned for axions have swept frequency ranges for decades. The EDMX project in the United States, cooled to near absolute zero, has listened patiently for the faint whisper of photons that would mark an axion's presence. Hints come and go, but the signal remains elusive. Other experiments, like CASA at CERN, try to catch axions emerging from the Sun, while new designs hope to broaden the search into unexplored ranges. Each negative result narrows the window, leaving smaller and smaller spaces where axions might hide. Sterile neutrinos, too, have danced on the edge of confirmation. An unexplained X-ray line at 3.5 keV, reported in 2014 in galaxy clusters, raised the possibility of their decay. Follow-up observations with other telescopes produced conflicting results. Reactor experiments sometimes hinted at anomalies in neutrino oscillations, then failed to repeat them. The story has become a cycle of hope and caution, each claim followed by debate, each excitement tempered by doubt. Primordial black holes share the same fate. Microlensing surveys limit their numbers. The cosmic microwave background constrains their abundance. Gravitational wave detections raise speculation, then meet with alternative explanations. They remain possible in certain ranges but never confirmed. You stand at this point in history surrounded by detectors that listen in silence, telescopes that record distortions but never a direct glimpse, theories that multiply as evidence refuses to choose among them. The paradox is sharp. Gravity proves dark matter beyond doubt, yet no experiment has placed a face on it. The reasons lie in the very nature of the candidates. If WIMPs exist, their interactions are so rare that even a massive detector may record only a handful of events in years. If axions exist, their coupling to photons is so faint that decades of scanning may be required. If sterile neutrinos exist, their signature may be buried in background noise or smeared across cosmic distances. And if primordial black holes exist, they may lurk only in narrow mass windows that current instruments struggle to probe. Some physicists take the silence as encouragement to push harder, to build bigger detectors, to wait longer. Others take it as a hint that perhaps the answer lies elsewhere. New forces, hidden sectors, or a revision of gravity itself. Modified theories like MOND or emergent gravity try to explain galactic motions without dark matter, though they falter against evidence like the Bullet cluster. Still, their persistence reflects the unease that decades of searching have not found what everyone expects. The lesson is sobering. Discovery is not guaranteed, no matter how strong the case for existence may seem. Nature does not promise to reveal its secrets on human timescales. Dark matter may remain invisible for another decade, another century, perhaps longer, or it may be revealed suddenly by a single unmistakable signal. For now, the story ends in patience. The weight of galaxies proves the unseen is real, but the unseen refuses to be named. The silence of experiments would be troubling enough, yet the deepest challenges to dark matter arise not in laboratories, but in the sky itself. Computer simulations based on the standard lambda CDM model predict a universe filled with structure, branching like a cosmic forest. In these digital universes, large galaxies like the Milky Way are surrounded by swarms of smaller companions, hundreds of faint satellites orbiting like bees around a hive. The problem emerges when telescopes turn from simulation to reality. The Milky Way and its neighbour Andromeda do have satellite galaxies, but not nearly as many as theory demands. By some estimates, simulations predict 10 times more companions than are observed. This mismatch is called the missing satellites problem. It has haunted cosmology since the 1990s, when numerical simulations became detailed enough to track small-scale structure. The absence is not subtle. When you look at the sky through modern surveys, you see dozens of faint dwarf galaxies, some so dim that only their stars betray their presence. Yet the simulations demand hundreds. If dark matter halos truly formed in such abundance, where are their visible counterparts? The paradox is sharp. The invisible glue that holds galaxies together also seems to create more structures than telescopes can find. Astronomers have searched for explanations. One idea is that many halos exist, but they remain dark because they fail to form stars. Gas might have been stripped by ionization in the early universe, or blown away by supernova winds, leaving behind invisible clumps of dark matter. These starless halos would still exert gravity but remain undetected by light. Another possibility is that surveys simply have not reached faint enough limits, and many ultra-dim dwarfs still wait to be discovered. Indeed, projects like the Dark Energy Survey and Pan-STARRS have uncovered new satellites in recent years, raising the count but not enough to erase the gap. The missing satellites problem reaches beyond simple counting. It questions whether the lambda CDM model, so successful on large scales, struggles on small ones. You stand in a universe where the grand architecture of clusters and filaments fits the model beautifully. Yet the neighbourhoods of galaxies look sparse compared to predictions. The contrast makes the paradox even sharper. The theory works on the largest scales, but falters in the details of the smallest. This tension does not overturn dark matter, but it forces cosmologists to refine the story. Some add feedback processes, modelling how supernovae and radiation suppress star formation in tiny halos. Others test warm dark matter, particles that move faster than the cold variety, smoothing out small structures before they can form. The debate continues, because the sky offers no easy resolution. For now, the missing satellites problem remains one of the clearest reminders that even the most accepted models leave gaps. The galaxies that should be there are not, and the universe offers no simple explanation. Another challenge rises not from the outskirts of galaxies but from their very hearts, where theory predicts sharp peaks of invisible matter, while telescopes reveal softer cores. This tension is called the cusp core problem, and it has troubled cosmology since the 1990s, when simulations of cold, dark matter grew detailed enough to resolve the inner regions of galaxies. In numerical experiments, halos of dark matter form with steep central cusps. The density rises dramatically toward the centre, producing a pointed profile. Yet when astronomers measure the rotation of dwarf galaxies and low surface brightness galaxies, the data tell another story. Instead of steep increases, the central mass distribution appears flatter, forming a core. The difference is not a small detail, but a clear mismatch between theory and observation. You look at a dwarf galaxy through the lens of a telescope. Faint stars stretched thin across the sky. Its rotation curve should spike near the centre if a cusp dominates. Instead, the curve levels off, suggesting a smoother distribution of mass. The invisible halo does not seem to follow the sharp profile of simulation. The contrast becomes sharper when many dwarfs show the same pattern. Explanations multiply. One idea is that baryonic physics, the messy processes of ordinary matter, reshapes the halo. Supernova explosions could blast gas outward, stirring the central regions and softening the cusp into a core. Feedback from star formation and radiation might redistribute matter, erasing the steep profile predicted by pure dark matter simulations. Another possibility is that the simulations themselves miss complexity, too idealized to capture turbulence, feedback, and the richness of galaxy evolution. Alternative models of dark matter also appear in this debate. Warm dark matter, with particles moving faster than the cold variety, naturally produces smoother cores by washing out small-scale structure. Self-interacting dark matter, where particles collide with one another more than standard models allow, could redistribute mass in the centre, softening cusps into cores. Each scenario has strengths, yet none has won decisive support. The cusp core problem is more than a technical mismatch. It is a reminder that the unseen cannot be separated from the visible, The gravity of dark matter sets the framework, but the violence of supernova, the churn of gas, and the birth of stars all leave their marks. The heart of a galaxy is not only a dark matter laboratory, but also a theatre of ordinary processes. Without understanding both, the profile remains blurred. By the 2000s and 2010s, better data poured in from radio telescopes and optical surveys. The evidence for cores in dwarf galaxies grew harder to dismiss, yet the diversity of galaxies complicated the picture. Some dwarfs show steep cusps, others broad cores, hinting that multiple processes may be at work. No single explanation fits all, leaving the problem alive. You live in a cosmos where galaxies form and evolve through layers of interaction, some visible, some not. The cusp core problem sits at the crossroads of those layers, a puzzle born from the meeting of theory and observation. It teaches that the invisible glue is not simple, that its behaviour may be tangled with the fire and wind of ordinary matter. For now, the centres of galaxies remain places where theory falters. The sharp cusps of simulation and the flat cores of observation do not align. The solution may lie in better data, better models, or in a new understanding of what dark matter truly is. Until then, the tension at the heart of galaxies continues to remind us that the universe still keeps part of its weight hidden in mystery. If dark matter fails to fit every detail, some scientists argue that perhaps the problem is not with the unseen mass, but with the law of gravity itself. The idea is bold. Maybe galaxies rotate strangely not because of hidden particles, but because our equations for gravity are incomplete. This line of thought gave rise to MOND, modified Newtonian dynamics, first proposed by Mordechai Milgrom in the early 1980s. MOND begins with the simple premise. At very low accelerations such as those felt by stars in the outer regions of galaxies, the force of gravity might not follow the familiar inverse square law. Instead, it could weaken more slowly, giving stars extra pull without the need for dark matter. When Milgrom applied his equations to galaxy rotation curves, they matched the data surprisingly well. No invisible halos were required, only a tweak to gravity's behaviour on the smallest accelerations. The appeal of MOND lay in its predictive power. Without invoking new particles, it reproduced flat rotation curves and even predicted the relation between galaxy mass and orbital speed, now called the baryonic Tully-Fisher relation. For small, isolated galaxies, the fits were impressive. It seemed that perhaps gravity itself was whispering that it had another layer. Yet problems appeared as the scope widened. MOND handled individual galaxies well, but struggled with galaxy clusters. The velocities of galaxies within clusters demanded more mass than MOND could provide, even with its altered law. Gravitational lensing too revealed mass distributions that could not be explained without some form of invisible matter. To preserve the idea, extensions were built, relativistic versions like TVIS, tensor vector scalar gravity, that tried to align MOND with Einstein's relativity. Still, the evidence from clusters and the cosmic microwave background kept pressing back. Modified gravity theories multiplied. Some explored FR gravity, where Einstein's equations are generalized to allow new curvature terms. Others proposed emergent gravity, suggesting that gravity itself is not fundamental, but arises from deeper thermodynamic principles. Each theory promised to erase the need for dark matter, yet each faced hurdles when confronted with the full range of cosmological data. You stand at this crossroads in the debate, reading graphs where MOND curves fit beautifully to dwarf galaxies, then falter in the face of galaxy clusters. The elegance of the idea draws the eye, but the sky insists on something more. The bullet cluster in particular dealt a heavy blow. showing mass and light separating during collision, something modified gravity alone could not explain. The persistence of these alternatives matters. They remind cosmology that dark matter is still a hypothesis, not a direct detection. They force every piece of evidence to be weighed carefully, not assumed. And they highlight the deeper question: are we missing a particle, or are we misunderstanding a law? For now, modified gravity remains a provocative alternative, tested, refined, and debated. It explains some puzzles elegantly and fails others stubbornly. Its role is not to replace dark matter entirely, but to keep the field honest, to remind us that the universe might still resist the neat categories we prefer. When all the challenges are gathered together, the picture is not of tension. A theory that explains the universe on grand scales yet stumbles in the fine details. The Lambda CDM model stands as the dominant framework of cosmology, able to describe the growth of structure, the shape of the cosmic microwave background, the acceleration of expansion, and the distribution of galaxies across billions of light years. Yet within this broad success lie cracks that refuse to close. The missing satellites problem shows the sky emptier than simulations expect. The cusp core problem reveals that galaxies hold flatter centers than theory predicts. Modified gravity steps forward with elegant mathematics, only to be pushed back by clusters, lensing, and the bullet cluster. Each of these challenges is sharp enough to keep cosmologists awake, not sharp enough to overturn the model. You watch as new surveys widen the horizon. The Dark Energy Survey finds faint dwarfs once hidden. The Pan-STARRS project adds more. Radio telescopes refine the motions of hydrogen clouds in dwarfs, sharpening the picture of their mass profiles. Yet with every new discovery, the core problems remain. The galaxies are still too few, their centers are still too flat, and the unseen mass is still only inferred. The Lambda CDM model survives not because it is perfect, but because it unites more evidence than any rival. On scales of clusters and filaments, it performs beautifully. On the backdrop of the cosmic microwave background, it matches with precision. On the growth of structure over billions of years, it fits the data. No alternative has achieved the same reach, and so the model endures, not unchallenged, but unbeaten. For you, living in this era, the tension is part of the story. You look at the night sky and see constellations, but behind them is a theory that works everywhere except where detail matters most. The paradox is almost poetic. The larger the canvas, the smoother the fit. The closer the view, the rougher the mismatch. Some physicists take comfort in this balance, arguing that baryonic feedback, star formation, and turbulence may one day close the gaps. Others see it as a sign that something deeper waits, perhaps in the form of new physics. Either way, the problems with dark matter reveal that cosmology is not complete. It is a work in progress, written both in equations and in unanswered questions. The block of evidence stands tall, yet the cracks are visible. Until new data fills them, the story of dark matter remains one of triumph, shadowed by mystery. The shadows of dark matter were already unsettling, but the greatest surprise came when astronomers discovered that the universe itself was racing apart faster and faster. For decades the assumption was clear. After the Big Bang, expansion would slow under the pull of gravity. Whether it would stop, reverse, or stretch forever was unknown, but the expectation was deceleration. In the late 1990s, that expectation collapsed. Two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure the expansion rate with unprecedented accuracy. Their tools were type Ir supernovae, exploding white dwarfs that flare with a consistent brightness. Because they shine with nearly uniform luminosity, they can serve as standard candles, measuring cosmic distances across billions of light years. By comparing their true brightness with their apparent faintness, astronomers could calculate how far away they were, and by measuring their redshift, how fast the universe had expanded since their light was emitted. The results, published in 1998, shocked the scientific community. The supernovae were dimmer than expected, meaning they were farther away than the decelerating universe allowed. Instead of slowing, expansion was accelerating. Space itself was stretching faster as time passed. The idea was so radical that many resisted at first, checking the data again and again, but the signal held. The conclusion was unavoidable. Some new component, repulsive in effect, dominated the cosmos. You stand in that moment of revelation, looking at plots where distant supernovae drift above the predicted curves. The graphs are not abstract. They carry the weight of the sky itself. Thousands of photons gathered by telescopes in Chile, Australia and Hawaii, each point a star that exploded billions of years ago. Together they shout a message across time: the universe is not slowing down. The shock soon transformed into a new vocabulary. Cosmologists began to speak of dark energy, a term meant less to explain than to acknowledge ignorance. It was the unseen opposite of gravity, a pressure built into the fabric of space. Within a few years, the discovery reshaped cosmology. Models that once considered only matter now had to add this new force, and the balance of the universe shifted. About 2/3 of everything was now assigned to dark energy. In 2011, the Nobel Prize in Physics was awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees for the discovery. By then, the evidence had expanded, confirmed by measurements of the cosmic microwave background and large-scale structure. What began as a surprising anomaly in 1998 had become the cornerstone of cosmology. For you, the lesson is as disquieting as it is profound. The night sky does not merely stretch into distance, it accelerates away, carried on an invisible current that no hand can touch. The discovery of 1998 showed that the universe is not only larger than you imagine, but stranger in its very motion. The power of the discovery rested on a single kind of star, one that dies in silence and then explodes with a brilliance so uniform that it became a ruler for the cosmos. These are type Ia supernova, the standard candles of astronomy. Their origins lie in binary systems where a white dwarf siphons matter from a companion star. When the dwarf reaches a critical mass, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit, the pressure triggers runaway fusion, igniting the star in a thermonuclear explosion. The result is catastrophic for the dwarf, but a gift to science, a flash of light bright enough to be seen across billions of light years, and consistent enough to serve as a measure of distance. For decades, astronomers suspected that such events could serve as cosmic yardsticks. Henrietta Leavitt's early 20th century discovery of the period luminosity relation in Cepheid variables had already shown the power of standard candles. Type Ia supernovae were the next step, brighter and more reliable for the deepest reaches of the universe. By the 1980s and 1990s, surveys with ground-based telescopes had begun to collect them in significant numbers. The breakthrough came when the two teams of the 1990s focused their efforts on building precise samples. The Supernova Cosmology project, led by Saul Perlmutter, used telescopes in Chile and the United States. The High-Z Supernova Search Team, with Brian Schmidt and Adam Rees, worked with telescopes in Australia and Hawaii. Both relied on careful calibration, cross-checking the brightness of nearby supernovae against known Cepheids to fix the scale. Once the method was stable, they pushed outward, measuring supernovae at redshifts of 0.5 and beyond, light emitted when the universe was only about half its current age. The data were relentless. Plot after plot showed distant supernovae appearing fainter than expected. The only explanation was that they were farther away than a decelerating universe would allow. The teams hesitated, knowing the implications, but the signal grew too strong to deny. When the paper appeared in 1998, they carried with them a shockwave that rippled through cosmology. You imagine being in the control room of one of those observatories, watching data stream from a night of observation. A single point of light, faint on the detector, carries the memory of a star that exploded billions of years ago. Combine it with dozens of others, and the pattern emerges: acceleration. The feeling is not only scientific but visceral, as if the cosmos itself were speaking in brightness and distance. Recognition came slowly but firmly. By the mid-2000s, follow-up surveys confirmed the effect with larger samples, and data from the cosmic microwave background supported the same conclusion. In 2011, the Nobel Prize in Physics went to Perlmutter, Schmidt, and Rees. The award acknowledged not just the measurement, but the courage to believe the data. Few discoveries in cosmology had turned expectations upside down so completely. For you, Type Ia supernovae are more than exotic explosions. They are the reason we know that dark energy exists. Without them, the universe might still be thought to be slowing under gravity's hand. With them, the story of cosmic acceleration is written in light that crossed the darkness for billions of years before reaching a telescope. The prize marked the moment when a faint flicker on a detector became a cornerstone of modern science. With discovery came the need for language, and cosmologists turned to a single parameter, written as W, to capture the nature of the force that drives acceleration. In cosmology, W is the ratio of pressure to energy density, a deceptively simple fraction that carries the fate of the universe in its value. For ordinary matter, pressure is small compared to density, so W is close to zero. For radiation, which streams at light speed, pressure is significant, giving W equals 1/3. Dark energy, however, demanded something stranger. To cause acceleration, it needed strongly negative pressure, enough to overcome the attractive pull of gravity. The simplest case, a constant vacuum energy filling space, gives W equals -1. This value quickly became the benchmark. Supernova data fit it well. The cosmic microwave background, mapped by the WMAP and Planck satellites, supported it. Galaxy surveys tracing baryon, acoustic oscillations added the same conclusion. W is very close to -1. Within that number lies a quiet revolution. A pressure as negative as its density is positive creates the effect of anti-gravity, pushing galaxies apart instead of drawing them together. You consider the implications. If W is exactly -1, then dark energy may simply be the cosmological constant first imagined by Einstein in 1917. A fixed energy of the vacuum, unchanging in time or space, simple yet profound. But if W deviates even slightly, the picture shifts. A value greater than -1 might mean a dynamic field, slowly rolling and evolving, what theorists call quintessence. A value less than -1, sometimes called phantom energy, leads to a universe where expansion grows so fast it could eventually tear galaxies, stars, planets, and even atoms apart. Measurements today pin W near -1 with impressive precision, but uncertainty remains. The margins are narrow yet crucial. A shift of a few percent could redraw the cosmic future. For this reason, enormous effort is poured into refining observations. The Dark Energy Survey, DESI, and the upcoming Euclid mission from Europe all aim to narrow the error bars. Every supernova, every galaxy cluster, every acoustic oscillation adds another data point in the attempt to trap her more securely. The elegance of the parameter lies in its simplicity. One number, pressure divided by density, stands as a code for the most mysterious force in cosmology. Yet behind the neat symbol is an abyss of interpretation. Is W exactly -1, revealing a constant vacuum energy, or does it evolve, whispering of new physics beyond the standard model? For now, the best answer is caution. Data align with W equals -1, but the door is not closed. Cosmology lives in those margins, where uncertainty becomes possibility. The universe, for all its expansion, has not yet expanded into clarity. Behind the number W lies a deeper divide. Is dark energy a simple constant in the fabric of space, or is it a field that shifts and evolves with time? The first option is the cosmological constant symbolized by lambda, an idea that reaches back to Einstein in 1917. The second is quintessence, a dynamic form of energy that changes its strength as the universe grows. Both explain acceleration, yet they tell very different stories about the past and future. The cosmological constant is the most economical explanation. It assumes that empty space itself carries energy, a fixed density that does not dilute as the cosmos expands. In this picture, galaxies drift farther apart forever, their recessions speeding up in a steady way. The simplicity of lambda matches observations so far, with W measured close to -1, yet it comes with problems. Quantum field theory predicts a vacuum energy vastly larger than observed, off by more than 100 orders of magnitude. This mismatch, sometimes called the cosmological constant problem, is one of the sharpest puzzles in modern physics. Quintessence takes another path. Instead of a constant vacuum energy, it imagines a new field spread across the universe, rolling slowly down a potential like a ball on a shallow slope. The field's energy density decreases with time, and its equation of state W can differ from -1. If the slope is steep, W changes quickly. If shallow, it may mimic a constant for billions of years. Quintessence can adapt to data and avoid some of the fine-tuning issues of lambda, but it introduces new unknowns. What is the field? What gives it its potential? And how does it fit with particle physics? You stand between these visions. If lambda is correct, the universe's fate is quiet but relentless. Expansion continues forever. Galaxies drift apart until they slip beyond visibility, stars burn out, and the cosmos cools into darkness. If quintessence is true, the story could differ. Expansion might slow if the field weakens, or accelerate even more if it strengthens. In some models, the field leads to a big rip, tearing even atoms apart. In others, it fades, leaving the universe dominated once again by matter. Observations so far do not distinguish clearly between these paths. The data lean toward lambda, but the margins allow quintessence to survive. Projects like Euclid and the Vera Rubin Observatory aim to tighten those margins, mapping billions of galaxies to catch the subtle differences in how structure grows. If W is not exactly -1, quintessence may rise from speculation to reality. For now, the contrast between lambda and quintessence remains one of the most profound divides in cosmology. One represents simplicity, the other dynamism. Both carry uncertainty, both shape how we imagine the future. The choice is not yet made, and the sky itself holds the answer. The future of the universe depends on which path dark energy follows, and among the possibilities, the most dramatic is the vision of a cosmos that tears itself apart. This scenario is called the Big Rip. It grows from the idea that the equation of state parameter W could be less than -1, a value sometimes called phantom energy. In such a universe, expansion accelerates not at a steady pace but ever faster, feeding on itself until it overwhelms every bond in nature. The sequence is chilling in its clarity. First, galaxies recede beyond the reach of light. Then, as acceleration increases, the pull of clusters weakens and galaxies themselves are unbound. Stars that once circled calmly are left adrift as their galaxies dissolve. Planets lose their orbits, solar systems unravel, and finally even molecules and atoms are ripped apart. In the final instance, space-time stretches so violently that no structure survives. You stand beneath the night sky and imagine its future under this law. The constellations you know would vanish, not by burning out, but by racing away faster than light could carry their image. The Milky Way, once a home, would fragment, its stars scattered into an expanding void. Long before the end, the sky itself would empty, leaving only darkness pierced by the fading glow of the local stars, until they too were torn from one another. The mathematics is simple, though merciless. If W is less than -1, the scale factor of the universe grows toward infinity in a finite time. Calculations suggest that if dark energy is phantom-like, the Big Rip could occur tens of billions of years from now. In that timescale, humans will be long gone, but the vision remains terrifying because it describes a universe that not only expands but destroys structure as it does. The idea was first articulated in the early 2000s by Robert Caldwell and collaborators. They showed that phantom energy leads inevitably to a singular end, one that contrasts with the gentler Big Freeze or the cyclical Big Bounce. The Big Rip is unique in its violence. Instead of a slow fading, it promises dismemberment of every scale, from clusters down to atoms. Some take comfort in the fact that current data do not require W to be less than -1. Most measurements place it close to -1, consistent with a cosmological constant. Yet the margin of error leaves room for phantom energy. It cannot be ruled out. Future surveys may narrow the range, but until then, the Big Rip remains a possibility written into the equations. The scenario forces reflection. If nature allows such a fate, then permanence is an illusion. Galaxies, stars, even the atoms that form bodies and thoughts are temporary, not because of decay, but because space-time itself betrays them. The universe does not collapse or fade, but rips itself apart, leaving no survivor to remember. There is another vision of the end, less violent but no less final. A future where the universe does not rip itself apart, but instead drifts slowly into silence. This scenario is known as the Big Freeze, or the heat death of the cosmos. It does not arrive with explosions or rips in space-time. It comes gradually, as expansion continues and energy is spread thinner and thinner, until nothing remains to fuel change. The principle behind the Big Freeze is simple thermodynamics. Every process in the universe depends on differences: hot against cold, dense against sparse, ordered against disordered. Over time, those differences fade. Stars burn their fuel and die. Black holes swallow what remains and slowly evaporate through Hawking radiation. Gas clouds thin, galaxies drift farther apart, collisions cease. In the far future, the cosmos becomes a thin mist of cold particles spread so widely that no new structures form. You stand in that distant era in thought. The night sky that once blazed with stars is empty. the Milky Way has merged with Andromeda and then dissolved into isolation. The last stars burn dim red, then flicker out, leaving only the faint glow of white dwarfs and neutron stars. Even those remnants cool into black dwarfs, silent corpses of suns. For trillions upon trillions of years, the universe is a graveyard lit by no new fire. The mathematics extends the vision. As the scale factor grows, temperature drops asymptotically toward absolute zero. Entropy climbs, reaching a maximum where no usable energy remains. In this state, time loses meaning, because change itself has stopped. The arrow of time, driven by entropy, has reached its destination. What remains is not an event but a condition: eternal stillness. The Big Freeze is not speculative in the same way as the Big Rip. It follows naturally if dark energy is a cosmological constant, with W equals -1. In this case, expansion accelerates steadily, but not violently. Galaxies drift apart beyond visibility, but local structures remain bound for immense spans of time. Only in the very far future do stars exhaust their fuel and black holes evaporate. The timeline is unimaginable. 10 to the power of 14 years for the last stars to fade, 10 to the power of 100 years for black holes to vanish. Yet physics allows us to trace that horizon, even if no observer will remain to confirm it. For humans, the idea is unsettling in a quieter way than the Big Rip. It does not describe sudden violence but endless decline. Life depends on free energy, and in the heat, death there is none. No engines can run, no cells can live, no thoughts can spark. The cosmos is not torn apart but drained of possibility. The Big Freeze reminds us that survival in the universe is tied not only to matter, but to entropy. As order fades, so does motion, structure, and meaning. It is an ending written not in catastrophe, but in exhaustion. There is, however, a vision opposite to exhaustion, one where expansion does not last forever, but turns back into collapse. This scenario is called the Big Crunch. It imagines a universe that grows for billions of years only to reverse direction, shrinking back into the heat and density from which it began. The idea was natural in the mid-20th century, before dark energy was discovered. If the total density of matter and energy exceeded a certain critical value, gravity would be strong enough to halt expansion. Once stopped, the cosmos would contract. Galaxies would draw together, clusters would merge, and the temperature of space would rise. In the final stages, stars and planets would be torn apart as space-time folded inward, ending in a singular state of unimaginable density. You look up at the sky with this future in mind. The galaxies now racing away would one day slow, then pause, then drift back toward one another. The night sky would brighten as galaxies crowded closer, collisions multiplying, starbursts igniting. What expansion spread thin, contraction would gather again, until the universe became a furnace. Equations of general relativity allow this path. If the density parameter omega is greater than 1, the universe is closed, curved like a sphere and destined to recollapse. Early measurements in the 20th century searched for this critical density, weighing galaxies, mapping clusters and counting light. For decades the balance was uncertain. The possibility of a big crunch stood as a real future, one mirrored by myths of cyclical creation and destruction. The discovery of acceleration in 1998 made the crunch less likely. With dark energy dominating, the cosmos appears fated to expand without end. Yet the scenario is not erased completely. If dark energy weakens or changes sign, its repulsion could fade. Gravity could once again dominate. In such a case, the universe might still halt and collapse. The Big Crunch carries with it a strange symmetry. The cosmos begins in a hot, dense state, expands, cools, and then returns to heat and density. The end mirrors the beginning. Some even suggest that such a collapse could ignite a new Big Bang, making our universe one cycle in an endless chain. For now, data point away from this fate. Observations of the cosmic microwave background, supernova and galaxy surveys all suggest that the density of matter is not enough to reverse expansion. Dark energy keeps acceleration alive, yet physics leaves room for change, and the equations do not forbid reversal. The Big Crunch lingers as a reminder that the universe is not bound to one story. Collapse remains written in the mathematics, even if nature has chosen another path. Some cosmologists take the idea of collapse further, asking if an end could also be a beginning, and if the universe might breathe in endless cycles of death and rebirth. This vision is called the Big Bounce, and it suggests that our cosmos may not be unique but one chapter in an infinite sequence. The concept has deep roots. Ancient myths spoke of eternal return, worlds rising and falling like seasons. In physics, the bounce gained traction in the 20th century as scientists wondered if a collapsing universe might rebound instead of ending in singularity. Instead of the Big Bang as an absolute start, it would be a bounce from a previous crunch. Expansion follows contraction, then contraction again, like the heartbeat of eternity. In classical general relativity, the idea faces difficulty. Collapse tends to end in singularity, a point of infinite density where the laws of physics break down. But modern theories, especially those involving quantum gravity, offer loopholes. Quantum effects at extreme densities could prevent singularity, replacing it with a rebound. Loop quantum cosmology, for example, predicts that space is discrete at the smallest scales, and this discreteness may allow the universe to bounce instead of crush. You walk through this vision and feel its rhythm. Galaxies expand and drift apart, then ages later they fall back together. Heat rises, density grows, but at the moment of maximum compression, the fabric of space-time pushes back and a new expansion begins. Stars ignite again, galaxies form again, and a new night sky is written. The universe has no absolute beginning or end, only cycles without number. Observations so far do not confirm or deny this story. The cosmic microwave background carries hints that some irregularities might reflect events before the Big Bang, though evidence remains thin. Some models propose that dark energy itself could trigger cycles, driving expansion now but turning to contraction in the future. Others invoke extra dimensions, suggesting that our universe might collide with another in a higher dimensional space, each collision birthing a new expansion. The Big Bounce remains speculative, yet it appeals because it softens the riddle of origins. Instead of asking why there was something rather than nothing, it asks only what stage of the cycle we inhabit. The paradox of a singular beginning fades if beginnings themselves are illusions. For now, cosmology cannot confirm such cycles. The data favour expansion without end consistent with a cosmological constant. Yet equations allow for richer possibilities, and imagination keeps them alive. The bounce endures as a reminder that the fate of the universe may not be a line but a circle, drawn across timescales so vast that even stars are brief sparks within it. The cycles of theory inspire wonder, but the daily work of cosmology is grounded in a harder truth. Billions of dollars are spent to search for things that have never been seen. Governments fund laboratories buried under mountains, satellites orbiting Earth, and observatories scanning the sky, all in pursuit of dark matter and dark energy. These investments are not made lightly. They represent faith in evidence drawn from gravity's pull, the bending of light, and the expansion of space. Yet the quarry remains invisible. Deep beneath rock and soil, shielded from cosmic rays, lie some of the quietest places on Earth. There, experiments try to detect WIMPs, weakly interacting massive particles. Tanks of liquid xenon, argon, or germanium crystals wait for the rare moment when one of these particles collides with an atomic nucleus. The signal would be a tiny flash of light, a faint vibration, an almost imperceptible recoil. Detectors like Lux in the United States, Xenon 1T and its successor Xenon T in Italy, and Panda X in China push sensitivity to levels once thought impossible. Yet despite decades of listening, the silence continues. The possibility remains, but the proof has not arrived. In the skies above, other instruments search for indirect signs. Gamma-ray telescopes watch the galactic center, hoping to catch excess radiation from dark matter annihilation. Neutrino observatories point toward the Sun, testing if captured dark matter particles might decay in its core, and the Large Hadron Collider, buried near Geneva, smashes protons at near light speed, hoping that exotic particles may appear in the debris. Each method closes part of the parameter space, narrowing where dark matter can hide. Dark energy requires different tools. It cannot be caught in a tank or collider. Instead, its presence is inferred through cosmic cartography. Gravitational lensing maps the mass distribution of galaxies and clusters, showing how much invisible matter shapes the web. The cosmic microwave background, measured by satellites like WMAP and Planck, provides snapshots of the early universe, revealing how dark matter and dark energy influenced its growth. Every tiny ripple in that faint glow carries information about density, curvature, and expansion. New missions push the search further. The Dark Energy Spectroscopic Instrument, or DESI, began mapping the three-dimensional distribution of galaxies in 2021, aiming to trace baryon acoustic oscillations with unprecedented accuracy. The Euclid satellite, launched by the European Space Agency in 2023, looks outward with a different strategy: weak gravitational lensing and galaxy clustering across billions of light-years. And the Vera Rubin Observatory in Chile, set to conduct the legacy survey of space and time, will scan the entire southern sky repeatedly, building a movie of cosmic evolution that will sharpen our measurements of dark energy and dark matter alike. You stand in the middle of this search, part of a generation that spends vast resources to chase shadows. When you look at the night sky, you see beauty. When these observatories look, they see questions written in light and motion. The billions invested are not wasted curiosity, but the cost of trying to understand why the universe exists as it does. For now, the invisible remains unseen. The detectors hear silence, the telescopes measure distortions, the satellites count ripples, and still no single signal gives the answer. Yet each effort narrows the possibilities, tightening the net around the unknown. Cosmology advances not only through discoveries, but also through exclusions, drawing closer by ruling out what the dark cannot be. The search continues because the stakes are nothing less than the shape and fate of the universe. Billions are spent not on fantasy, but on the recognition that to know the unseen is to know the foundation of reality. Yet one question hovers over all this effort, sharp and unsettling. What if the unseen is not there at all? The galaxies move, light bends, and the universe accelerates. But perhaps these effects do not come from invisible matter and energy. Perhaps the fault lies in the laws we use to describe them. In the early 1980s, Mordechai Milgram proposed modified Newtonian dynamics, or MOND. He suggested that gravity itself might behave differently at very low accelerations, such as those in the outskirts of galaxies. Instead of inventing unseen particles, he altered the law. In this view, stars orbit faster not because of halos of dark matter, but because the force that holds them changes its form at faint scales. MOND fit many galactic rotation curves with uncanny accuracy, predicting relations like the baryonic Tully-Fisher law before they were fully observed. To its supporters, it was a sign that gravity itself whispered of hidden structure. Later, more sophisticated modifications arose. The TV's framework, tensor vector scalar gravity, tried to bring MOND in line with general relativity. Other theorists explored FR gravity, altering Einstein's equations with new curvature terms. Still others speculated about emergent gravity, in which gravity is not fundamental at all, but arises from thermodynamic principles woven into space-time. Each proposal carried elegance and creativity. Yet each faced the same problem. On the largest scales, from clusters to the cosmic microwave background, the universe still looked heavier than light allowed. Then came the deeper link to quantum physics. The cosmological constant, lambda, interpreted as vacuum energy, should have been huge. Quantum field theory predicts that every mode of every field contributes energy to the vacuum. Summed together, the result is larger than observations by more than 100 orders of magnitude. A mismatch so extreme it is called the worst prediction in physics. If dark energy is simply vacuum energy, then why is it so small? If it is not, then what field drives acceleration? Here the boundaries between cosmology and particle physics blur, and the riddle of the universe's expansion becomes tied to the riddle of quantum fields themselves. Some physicists ask a different question still. What if dark matter and dark energy are not separate entities but two aspects of the same phenomenon? This idea of a dark fluid or unified dark sector suggests that the invisible scaffolding and the invisible push may emerge from a single substance with unusual properties. Depending on its density and pressure, it could mimic matter in one regime and energy in another. Such models remain speculative, but they carry a strange appeal. Instead of two mysteries, one would suffice. You stand at the edge of these possibilities, where evidence is strong but interpretation is fragile. If dark matter and dark energy are illusions of flawed equations, then the decades of searching for phantom particles may end in vain. If they are tied to quantum vacuum, then physics must confront its greatest mismatch. If they are one substance, then the universe is simpler but stranger than imagined. The ultimate questions do not erase the evidence. Galaxies still move too fast, light still bends too much, the universe still accelerates. What changes is how we explain it. Whether through unseen particles, modified gravity, quantum vacuum, or a unified dark fluid, the riddle remains. What is clear is only that the cosmos refuses easy answers, and so the story closes not with resolution but with an open horizon. The sky above you is proof that something beyond ordinary matter shapes reality, yet its name is still unknown. The search may take decades, centuries, perhaps longer, but each observation brings us closer. Until the invisible is revealed, the universe remains both familiar and alien, a stage lit by stars yet ruled by shadows.